So their pallets are blue. They came to us about 2.5 years ago. They were interested in asset digitization. So that's enabling them to track the pallets individually. Currently, they treat them more or less like a liquid. So the pallets move around and they measure the volume of pallets in any given location. This means they don't have a great deal of visibility on how many pallets are in any given place. And they can't, because they can't track pallets individually, they can't get a sense of the cycle time distribution, which I should explain in a second. The graphic on the left here is the pallet network in Chile, which was where we rolled out the digital twin first in South America. So to give you a sense of the scale, I was thinking how I could sort of convey that. So the US digital twin that we've got in production runs on 190 machines. We simulate about 30 million, or we replay about 30 million movements per year, and about 1.5 terabytes of RAM involved. So it's a huge scale engineering effort, and it's taken several years to build. So pallets, the main thing that they're interested in with pallets is cycle time. So in a perfect world, they leave a service center, which is down here. They get, in this case, scanned out of the service center. They're putting the QR codes on pallets. They get sent to a manufacturer. The manufacturer loads it up. Say the manufacturer is Coca-Cola. They send all the Coca-Cola on the pallets to the retailer, say Tesco's, and then the pallets are collected from the retailer and brought back to the service center. So classic circular economy. And a key metric for Brambles is reuse. Cost of timber has gone up massively. They need to make sure every pallet is issued as many times as possible, which means they need short cycle times. Their business model, generally, they charge per issue. So they try to maximize the number of issues per pallet, which means they need short cycle times. So in a perfect world, it works like this, but things get more complicated. So you have things called dirty cycles. This is when, if the pallet is equipped with a QR code, the equipment fails, or it passes through a service center that hasn't been instrumented yet. The effect of that will be that two short cycles actually look like one long cycle. So the cycle time of the pallet will be greatly extended. So that's one of the challenges they have. And part of the work that we've been doing is to try and quantify the effect of that distortion. These are, just to give you a further sense of the complexity that pallets can lead to. So these are, on the left, you've got multi-issue cycles. And basically that's when the retailer reissues a pallet to another manufacturer without it going back through a service center. So you'll have many short cycles, 3 in this case, passing through retailers before it comes back to a service center with a scanner. Part of the reason for rolling out asset digitization is to track how often that happens. If you're only tracking volumes, it's very difficult to get a clear picture of when that happens. So the digitization of the asset gives you visibility of that. The chart on the right shows how that would work if we instrumented the manufacturers with scanners. So then you can actually see all 4 cycles, the 3 cycles nested within the larger service center cycle. So the digitization process is all designed to give visibility. Without that visibility, you get this effect. So the green bars are showing how cycle time for a given customer may be distorted to look longer than it really is. So you can see that it has a fatter tail down here. That means that a higher number of the pallets appear to have longer cycle times. And the main driver of cost in the pallet business is long cycle times. So being able to track that distribution over all of a customer's pallets is very important and can be done by digitizing the assets. Here's a little video of it, a very simplified version of this working, just to give you a sense of what happens. So you've got the service center, you've got manufacturers, and you've got retailers. They're passing pallets between them by replaying what's happening in the real world here on the left. And that generates a distribution of the cycle times here on the right. So this is a very simple implementation, but in the real twin, we have hundreds of thousands of locations, and there's about 400 million pallets in the digital twin being tracked. Okay, so tracking devices. So in order to get this visibility, they have 3 main options. And one of the things we've done is show them what the benefits of each option is. So you have declarations, which is the way the business has been run historically, which is about if you're a manufacturer and you send 10,000 pallets to a retailer, you fill in some paperwork to say that you've done that, and then you're charged up until the point that you declare that you've sent them on. This has all sorts of problems in practice with undeclared movements and data quality issues. So tags was the next option. Tags is QR codes, as I talked about before. This is now being rolled out across Chile, and the process of rolling it out in the US has also started. The digital twin technology is there to guide that rollout and to capture and analyze the data as it's produced. So tags are just QR codes that sit on the pallets, and ultras are GPS devices that actually sit underneath the pallets that give you even more accuracy. What this graph is showing is for the tags that actually the accuracy of the data you're getting depends very much on the variance of cycle time at each given location. So, not going into too much of the detail, depending on the use case of the data that the digital twin is gathering, you need a different level of rollout. So the density of the tags or ultras in the pool as a whole determines to some extent how accurate the data you get will be. So if only 10% of the pallets have GPS trackers, your cycle time readings will not be as accurate as if 20% of the pallets have trackers. What this shows is the level of imprecision you can expect from those different rollout strategies given the variation in the data. This is illustrating the benefits of doing this. So within digital twins, essentially what they're trying to do is increase visibility. And one of the things that's shown is the network structure. So the chart on the right shows you how their network is really structured, and we can build these month to month. And you can see that the very large one is a hub. That means that it has a very large number of connections. So this could be a very large service center or a leading manufacturer or a retailer that's reissuing many pallets. Those hubs are vulnerable because if anything happens to disrupt the flow at that hub, it will have a cascade effect on the whole network. The fact that we now have a digital twin means we can run simulations to see what would happen if these disruptions occurred, and the two charts on the left of that one are showing what happens under different disruptions, and that has been made possible by the data capture that we've done. The chart in the middle actually shows the implementation of different strategies to reduce the effect of the disruption. Maximizing sustainability. So interestingly for Brambles, because it's a circular economy, sustainability is really a commercial metric. So maximizing reuse increases their profits, and it also reduces the need for new natural materials. So it's a win-win for them to increase asset productivity and reuse, and the visibility that digital twins provide has enabled them to do that. One interesting thing I wanted to mention was that as the digital twin got rolled out, we actually had more and more data on how the digital twin should be further rolled out and the benefits it might bring. So it's become a kind of virtuous circle. As more and more data was harvested and more analysis was done, we had a clearer and clearer idea of the benefits of that data. So what this shows is different strategies for further rolling out digital twin in the US. So this includes instrumenting service centers. There's about 750 of those. Costs about £1 million to instrument a service center. There's different ways of doing it. Instrumenting some service centers rather than others will have different effects. So we've measured that in terms of precision and reach. Reach determines, well, how many customers are you going to reach if you roll out service instrumentation in these service centers, and precision tells you what the accuracy of the data is. Size of the bubble is the cost. So with the data they've already gathered through the digital twin, they can actually make decisions about how to most effectively ramp up further rollout of digitization. There's a testimonial. And just to conclude, I wanted to mention a lot of the work that we do is based on network science. This is a quote from Barabashi, where he's essentially saying that many different networks have the same mathematical properties. So that includes transportation networks, logistics networks, processes inside cells, the financial market, social networks. These all have similar dynamics, and there are similar tools for analyzing them. The chart on the left here is actually the physical internet, so all the routers and data centers of the internet, and the chart on the right is the World Wide Web that runs on top of that physical infrastructure. So the tools for analyzing both are the same, and it's exactly the same for pallet networks. Right, that's all I have. Thank you very much.
Our next question, Harry, is for yourself, is what models do you use for the predictive modeling? In this process, what are your bottlenecks overall? You're on mute if you're talking.
So is this Alvaro's question? I'm just looking at the board. So there's Alvaro's questions about with one massive service center, what analytical tools do you implement to explore disruption scenarios in your digital twin?
So it's the question above I was asking, but you can answer both together. The one in purple.
Okay. All right. Well, to the disruption stuff. So there are two real types of disruptions, like the classical disruption analysis you do. One is a targeted attack and the other is random. So a targeted attack is like, generally you select the node in the network which has the highest number of connections. So if you were modeling disruption in aviation, that would be like Heathrow. So what happens when you disrupt the hub? That's a targeted attack. That's one of the scenarios we run. And we'll run scenarios which disrupt the hubs, so the largest degree nodes, one after another, and then see what the effect of that is. The other one is random. So as the name suggests, it would just be you just disable a node in the network at random. So we take both those two approaches, and there are a couple of standard metrics that we use to track under that disruption, under that simulated disruption. One is just the size of the largest component. So networks should really work as one cohesive whole. And as you start removing hubs, they tend to break apart. And as they break apart, they become less efficient at whatever it is they're trying to do. The other one, which is a bit more supply chain specific, is you have two different types of nodes. You'd have supply nodes and demand nodes, for example. Demand nodes might be distribution centers, and the metric you track is the ratio of distribution centers that have access to a supply node. And that would be, as the disruption continues, that ratio decreases. And then in terms of the predictive stuff, I mean, we tend not to do a lot of predictive analytics, really. So we're trying to figure out how to make any given network less sensitive to prediction errors. So in a sense, we think that prediction is sort of the problem. Like, using this data to try and make predictions is part of the issue. And what we should really be doing is trying to find ways to manage the uncertainty that's inherent in the system. So the simulations we do create different scenarios where you try to measure the effect, and ultimately what you want to avoid is like accelerating cascade effects in a network, where a small disruption over here causes a huge problem down the line over here. And a lot of these networks have sophisticated prediction technology, but it only works as like a linear planning process. So long as the predictions are correct, everything works well. But the world just increasingly doesn't work like that. So the key thing is to be resilient across a range of uncertainty, and to not be too sensitive to errors in those predictions.
Brilliant. Thank you, Harry. That's really good.